Hello everyone, welcome to the exercise for MDO. Today we are on solution space optimization. Exercise 1 solution space. Find the largest rectangle x1L equals 0, x2L equals 0, x1U equals x1 and x2U equals x2 that fulfills both inequality constraints G1 and G2 at the same time. Design variables are x equals x1 and x2. Constraints are G1 less equals 0 and G2 less equals 0. In this diagram, you can see that we need to find a box with the maximum area. This corner of the box is already given by x1L and x2L, and we need to find the position of the top right corner of the box. As we can see, if this corner fulfills both constraints, all the other points in the box are feasible. And the corner can be either here on the boundary of G1 or here on the boundary of G2 or here on both the boundaries of G1 and G2. And the task is solve the KKT conditions for the Lagrange function while utilizing an active set strategy. Now, first we need to formulate our objective function. We want to maximize the area. This is x1 times x2, and as the objective function we want to minimize it. That means we need a minus in front of it. And the Lagrange function is L equals the objective function times mu1 times G1 plus mu2 times G2. And we just replace the formula for f and g. We get this. That means L equals minus x1 times x2 plus mu1 times bracket x2 minus bracket 4 minus 1 divided by 4 times x1 plus mu2 times x2 minus bracket 6 minus x1, and the derivative of the partial derivative of L1 to x1 is minus x2 plus quarter times mu1 plus mu2. It must equal 0, and the partial derivative of L to x2 equals minus x1 plus mu1 plus mu2 must also equal 0. And as we already shown in the last slides, the maximum error is achieved either only G1 is active. That means the top right corner of the box lies on the boundary of G1. 2. Both constraints are active. That means the corner of the box is exactly here at this point. And 3. Only G2 is active. That means the corner of the box lies on the boundary of G2 is somewhere here. Now the case 1, only G1 is active, and that means that G1 must equal 0 as the corner lies on the boundary of G1, and mu2 equals 0 because G2 is not active and we don't have to consider it yet. And then we still have these two equations. The solution of this equation system is that x1 equals 8, x2 equals 2, and mu1 equals 8. And with this solution we can see that G2 is bigger than 0, as we can see that x2 is 8, 8 minus 6 minus x1 is minus 2, and 8 minus 2 is 10, is bigger than 0. That means G2 is violated. That means it's not a feasible solution. When we draw the box, it's here. We can see that this box is not entirely in the feasible range. Case 2. Both constraints are active. That means G1 must equal 0 and G2 must also equal 0. And we have these two equations from the last slides. The solution is x1 equals 8 divided by 3, x2 equals 10 divided by 3, mu1 equals minus 8 divided by 9, and mu2 equals 32 divided by 9. We can see that mu1 is smaller than 0. This is not feasible, because the condition for mu1, mu2 is that they must be bigger than 0. In this case, the box lies here, and this is not the box of maximum area. Case 3, only G2 is active. This is similar to case 1, and we have here mu1 equals 0 because G1 is inactive, and G2 must equal 0, and plus these two equations, the solution is x1 equals 3, x2 equals 3, and mu2 equals 3. And if we check G1, we'll see that G1 is smaller than 0. And the box lies here. And this is a box of maximum area we are looking for. Exercise 2. Simple crash design problem. Engineering problem is: find the optimal wall thickness T in the interval 0.1 mm to 10 mm of the two parallel side bins of length L with respect to maximum weight M, while ensuring that all kinetic energy from a full frontal crash against a rigid barrier at the velocity v0 equals 50 km/h will be absorbed. And this is a side bins, and the cross section assumed to be a square with length A, and the thickness is T, and the material density is ρ. And in this table, the parameter of the geometry and the materials are listed. The first is the length of side bins. It's 300 mm. The weight of the car is 2000 kilo. The velocity at the beginning of the crash is 50 km/h, and the size of the cross section of the side bin A equals 80 mm. The density equals 2.7 gram per cubic centimeter, and the yield stress of the material is 216 MPa, and the force while the material start to form is F equals sigma yield times the area of the cross section. It is 4 times A minus T times T, and this stays constant during the crash. Now come to the tasks. Task 1. Solve the given optimization problem analytically. 2. In reality, the wall thickness T is subject to deviations due to manufacturing tolerances. How do these derivations impact passenger safety? Task 3. The thickness deviations follow a normal distribution with mu equals T2 star and sigma equals 0.1 mm. What is the resulting design mass if the failure rate is required to below 3.4 times 10 to minus 6? Now to task 1. We need to formulate our optimization problem first. Our design variable is T in the design space of 0.1 mm to 10 mm. Our objective function is the mass of the side bins. It is we have 2 side bins, and this is the area of the cross section, and this is L is the length. Then this is the volume of the side bin. This is the density. Then we have 2 times volume times density is the total mass of 2 side bins. We have the constraints that the energy, the kinetic energy must be absorbed in the frontal crash. That means the kinetic energy minus the energy absorbed by the side bins must sum 0. The kinetic energy can be calculated with the weight of the car and the velocity. That is weight times velocity squared divided by 2, and the energy absorbed by the side bins can be 2 times the force times the length, and the formula for the force is already given. It is sigma yield times 4 times A minus T times T, and with the 2 for 2 side bins and L for the length, we have in total that's G T equals E kin minus 2 times sigma yield times 4 times A minus T times L less equals 0. And then we have our optimization problem formulated as minimize Ft subject to Gt equals E kim minus blah blah less equals 0 Mt in its design space. And here is a plot of our objective function and the constraints. We can see as the thickness of the wall grows, the weight or the mass of the side bins will grow, and the value of the constraints will decrease. And the optimum is actually at the point where the constraints is just V0 here. And we can solve this optimization problem with the help of the Lagrange function. It is L equals Ft plus mu times G of t, and we will get this. And the conditions is the derivative of L to t must equal 0, and the constraint is active. That means G is also equal 0. The solution of t can be calculated along with the second equation, and we can find the solution of this equation at 2 points. The first one is t star equals 5 mm, and the second one is t equals 75 mm. Additionally, because t must in its design space and 75 mm is too big, so only the solution of 5 mm is feasible. And with this solution we can calculate mu star and the mass of the side bins, which is equals 2.41 kilo. Task 2. In reality, the wall thickness T is subject to smaller deviations due to manufacturing tolerances. How do these deviations impact passenger safety? First, we find the solution T star at the point that the side bins just absorb the kinetic energy in the crash. That means if T is smaller than T star, the side bins cannot absorb the complete crash energy. And then, as the passenger cell is assumed to be rigid, and it will lead to dangerous high values of deceleration after the two side bins are fully compressed. We have energy left. That means the passenger cell will have enormous deceleration. And by assuming a normal distribution of the thickness value around the design point T star, 50% of the cars will not provide sufficient passenger safety. As we see in this diagram, we have design of the wall thickness T at 5 mm. All the product with the wall thickness smaller than 5 mm cause a danger to the passenger. Task 3. The deviations follow a normal distribution with the mean mu equals T2 star and sigma equals 0.1 mm. what is the resulting design mass when the failure rate is required to be below 3.4 times 10 to minus 6. Let's have a look at the figure first. Overall, we need to find design wall thickness greater than 5 mm, so that the integration of the probability density function from negative infinity to 5 mm will be less than 3.4 times 10 to minus 6. Yeah, and with this idea, we see that the wall thickness is distributed normally with the mean equals T2 star, and the sigma is given, and the probability density function is this, and this can be found in many places. And our requirement is that the integration of the probability density function from negative infinity to 5 mm is less than 3.4 times 10 to minus 6, and this result a design of the wall thickness T2 star greater than 5.45 mm, and so that the mass of the side beams will be greater than 2.63 kilo. And it has to mention that this equation cannot be easily solved analytically, and we can get a solution with the help of MATLAB, and this is code to solve this equation. Exercise 3. Advanced crash design problem. The engineering problem is: find the largest region of permissible variations for F1 and F2 while satisfying the requirements A max smaller equal AC, E remain less equal 0, and order less equal 0. And this engineering problem has already been introduced in the lecture, and let's look further. The toy problem consists of two sections, section 1 and section 2, deform at constant collapse load F1 and F2 respectively. Only plastic deformation, that means no force, while D point less 0. That means if there's no motion, there will be no force. And the passenger cell is modeled as rigid. And we have the system equations, that is the acceleration of the car equals the force. The force can be either F1 or F2, it depends in which section the car is. And the xt equals d1 plus d2. That means the deformation of the car equals the deformation of the first section d1 and plus the deformation of the second section d2. System response are x d1 d2. The quantities of interest are first A max. This is a maximum acceleration of the car, and it is the force of the second section divided by the mass, and the remained energy E rem. This is the difference between the kinetic energy and the energy absorbed by the deformation, the possible absorbed energy. And we have then the kinetic energy is mass times velocity squared divided by 2, and the energy absorbed by the two sections is F1 times D1C plus F2 times D2C. This is the length of the sections. And the order is F1 minus F2. That means the deformation of the first section happens always before the deformation of the section 2. And here is the value for the parameters and also for the requirements. They are D1C, this is the length of the first section, it is 0.3 meter, and D2C is the length of the second section, is also 0.3 meter. The mass of the car is 2000 kilo, and the velocity before the crash is 56 km per hour, and the maximum acceleration is 32 g. And the design space for our design variables F1 and F2 is from 0 to 1000 kilonewton. Now to the tasks. Task 1. Formulate the objective function and 3 conditions with the box variable C equals F1L, F2L, F1U, and F2U. Task 2. Derive the quadratic engineering problem. And task 3. Derive the Lagrange-Newton equations for the quadratic optimization problem. Start with task 1. Formulate the objective function and the constraints. Now we are using actually the method corner checking here, because we defined the design variable as the corner of the design box. That is a lower bound for F1, lower bound for F2, upper bound for X1, and upper bound for X2. The objective function is that we need to find the maximum area of the box. That means this is the length of the box in the dimension F1, and the length of the box in the dimension 2, and the length in dimension F1 times the length in dimension F2 is the area. With a minus in front, we get the objective function. And the constraints with respect to C, firstly we need to formulate our constraints. That is, for all designs F1 and F2 in their design space, the 3 constraints need to be fulfilled. That is, the maximum acceleration must smaller than the requirement on it. Then the remained kinetic energy must less than 0, and the order must also be less equal 0. And we can rewrite these constraints to a matrix G times X less equal GC for all designs X in the design space determined by C. And the X, the design variables, is F1, F2, and G is like this. We can derive G easily from these three constraints, and also GC. Then the design space for X is the box. Yeah, and here we denote DC as the DC1, DC2 because they are equal. Now that we have the original constraints, we can start to rewrite it in the form of gamma times C smaller equal GC. And the definition for gamma can be found in the lecture. And with G defined, we firstly need to determine gamma 1. And gamma 1 is actually all the negative elements in G1, and the other elements are 0. And we can see that the element 0 comes to gamma 1 to 0, and 1 to 0 because 1 is positive, and we have the negative element -1. It will be taken by gamma 1, it's -1, and this -1 is same, and this 1 is positive, it turns to be 0 in gamma 1, and this -1 is negative, it will be taken. And for gamma 2, it only takes the positive elements in G. That is 0 comes to 0 and 1 is positive, it comes to 1. -1 is negative, it comes to 0. This -1 also comes to 0. This 1 is positive, it comes to 1, and -1 negative to 0. And we can construct gamma with gamma 1 and gamma 2. Yeah, and GC is the same as in the original constraints. So with gamma and GC, we have the three constraints with respect to our design variables C. That is an F2U smaller equal NAC minus F1L minus F2L smaller equal minus M times V0 squared divided by 2 times DC, and minus F2L plus F1U less equal 0. Now, how can we understand this? Let's take our original constraints. This is for all designs F1 and F2 in the design box determined by C. The constraints need to be fulfilled. Additionally, with the condition that all the designs are in the design box, we have these three equations. Let's take an example of the first constraints. F2 less equal n times AC, and we have additionally that F2 is less equal F2U. That means F2U is the largest design of F2, and to fulfill both of these equations, we just need to check if F2U is less equal m times AC. If FU2, the maximum value of FU, is less than m times AC, then all F2 will be less than m times AC. So actually we just need this in equation to replace the original constraints, and the same for the constraints 2 and constraints 3. And this is the end our derived constraints with the gamma. The next task derives a quadratic engineering problem in the form of minimize C transpose times Q times C subject to A times C less equal B and C in the design space. Now start with Q. We need to rewrite our objective function in the form of this. Yeah, and we can start with a formula for F. It is minus F1U minus F1L times F2U minus F2L, and we can expand it in one step. It comes to F1L times bracket F2U minus F2L. We get this, and then F1U times F2U minus F2L with a minus in front, then we get F1U times bracket minus F2U plus F2L. And this we can write it in the matrix form. It is the matrix, the vector F1L, F2L, F1U, F2U times F2U minus F2L and 0, then minus F2U plus F2L, then 0. And the vector on the right side, we can again expand it to a matrix times a vector. That is the matrix this times the vector of the design variables. Yeah, then we get Q equals the matrix here. Then we come to the constraints. As we already have our constraints in the form gamma times C smaller equal GC, we can easily see that A just equals gamma and B just equals GC. Now the last task derives the Lagrange-Newton equations for the quadratic optimization problem, and note that the matrix Q is here not symmetric. And the Lagrange equation is F plus mu times the constraints. And we have two conditions. First one is the derivative of L to the design variables C, it must be 0. And second, the constraints are active. That means A times C minus B must be 0. And these conditions at all constraints are active, we can easily see that we have constraints, one in the upper bound of the box and one referred to the bottom left corner of the box, and the third one refers to the bottom right corner of the box. They have to be or active to be able to restrict the size of the box. Now we can rewrite these two equations in the matrix form, that is Q transposed plus Q and A transposed A 0 times C and mu equals 0 and B. And here's to mention that the derivative of the function f here is C transposed times Q times C. Its derivative to C is T transposed plus Q transposed plus Q times C. Yeah. Now with this equation we can solve C and mu by inverse this matrix and times the matrix here, and we can just write it in detail. It will be our design variables and the mu for 3 constraints, and the matrix is like this, and this vector is like this. And we can solve this equation with MATLAB, and we will get the solution like this. And the first 4 elements determine the size and the position of the box. We can draw it in this plot. It will be this red box. And the solution is that F1 is in the range 291 to 516, and F2 in the range of 516 to 628.
Task 8.4 is a MATLAB exercise, so we will switch to MATLAB. So the tasks we will handle here in this exercise are we will use the design space projection tool to get a feeling for the solution spaces and for how the tool works, and we will change some bounds for certain values and have a look how this influences the overall performance. And we will also compare it to the task 8.3. So now let's switch to MATLAB. So here you can see the folder and the files which you can find on Moodle, and you start the X-ray tool by double-clicking on this MATLAB function, and then this MATLAB function opens and you press run. And then this drop-down menu opens, and here you open the MDO crash problem by clicking on it on the drop-down menu, and then we wait a second. then those two windows open. We have here the graphical representation of our solution space, and which is the design space projection, which you have learned in the lecture, and also some sliders here to assign values for the design variables. So what we do now is we will choose the values as they are set in the task 8.3. Okay, those which are the values 0.3, so we can just type in 0.3 for the lower bound of the design space, and as there's a point value also for the upper bound. And for the mass, we set the value of 2000. You can find those values on slide 16 of the exercise. Now we will press update, so the design space projection will be updated according to our values, because till now the projection is made over the complete design space, and now we narrowed down some design variables from an interval to a point-based solution. So we assume, accordingly to the lecture, that the frontiers or the border lines of the requirements will get sharper because we narrow it down to a point-based projection, or towards a point-based projection. Now let's see what happens by clicking the update button. And now we see that it's getting more, way more clearer as we've expected. And we also see that here we don't have intervals anymore, but concrete values and point-based solutions. And now we are at task 5. We have to change the intervals for F1 and F2 until it only contains green dots, which means that it contains only good designs. So to do that, we will use the slider here, and we'll have a look. So let's say we take the upper bound for F2 at around 6 and something, and the lower, let's say around 5. And then we press update and see what happens. So I think we got it quite well. So now we narrowed down this interval, and you can see in the other diagrams that green dots are appearing because we are getting closer to good designs. So it also has an influence on the other projections, of course. And now we still have to adjust F1, and so we will go to, let's say, something about 3 to 5. We'll update it. We see the upper bound for F1 is still a bit large, so we will narrow it down a little bit. Yeah, now it looks quite well. So it only contains green dots. So this is a solution for our design problem with the design space projection tool and a box-shaped solution space. When we compare this bounds with the results from task 8.3, which you can find on slide 23, we see that we are not as we do not reach the optimum design by doing it by hand, but we get quite close. So the optimum design here, or let's say the optimum in the sense of the largest permissible box. The lower bound is 291. We have 327, and for the upper 516, we have 518, quite close for the upper bound actually. And for the lower, we are about 500, which are 516 for the lower bound, and for the upper 628, and we have 629. So we are quite good actually with our design here, but you see this is something which is done by we did with the design space projection tool. This was not an optimization, so it was rather an interactive tool you can use, and it also helps you to get a feeling for the design problem and the influences of certain design variables, and how it influences the end result. So for example, you could also play around with the mass and lower the mass and see how this influences the overall system performance and results. And we see, okay, this requirement is violated here, which is the maximum acceleration, and we would have to adjust the other values. So you have the tool now, you can play around and try to change the parameters and get a feeling also how the other visualizations change. So that's it for today. Have a nice day and bye-bye.